Go.
All right, this is Team 12's image processing program.
Image processing is used mostly in biomedical engineering, yet you can find it in almost all concentrations of engineering in some way. These medical images in biomedical engineering are subject to noise, so noise canceling and edging helps to get a more precise image. This engineering can be used in medicine and biology. Society notes that imaging, processing, and analysis can be used to determine the diameter, volume, and vasculature of a tumor or organ. And to get into this field, you're going to need a degree in electrical engineering, computer science, or a related degree.
Okay, so the first thing we will be demonstrating is how our program handles an error.
So we're going to put in a file that does not work for our code, as you will see in a second. So this file did not work because our code recognized the file to not be a PNG and is actually a JPEG. So our code will now prompt us to import a proper file instead of a JPEG.
All right, and if we now insert a correct file, this is how our code runs, and we will describe how it's working.
So the first step is the grayscale. We decided to use the standard conversion formula for the grayscale. We use this formula because it does cut down on time a little bit. What it does is it takes the red, green, and blue parts of an image, plugs them into this formula, multiplies the color by the constants in the formula, and then adds these components together.
All right, so the next part is blurring or smoothing the image to get rid of the noise. So what we first do is create an array of zeros, like the size of the previously created grayscale image. And we decided to use a Gaussian filter to do this because it allows us to create more weight on the center pixels, which creates a smoother image versus the box image, which is just a simple averaging filter, which can often lead to other edge effects that we would prefer not to have. And basically what our program does, our function does here, is it looks at each pixel in the grayscale image. And what we do is we sum and average like this element-wise result that we created above and replace the pixel in that zero array that we made with this new value, which helps to create the blurred image.
The edge enhancement step takes the blurred image and highlights each edge while making the rest of the image black. This is done by first splitting the image into X and Y directions and then taking the maximums of each gradient in each direction. We use the kernels for each direction and then use the pixels needed to find the vectors. Once we find the vectors, we replace the old pixel value in a new array, which then creates the edge enhanced image.
And then the last step is thresholding. So first we fill an array with ones that's the same size as the previous image produced in the edge enhancement step. Then we compare each and every pixel of that image to our set threshold, which here we set to 50 over 255, but that may need to be changed by the user depending on which image is used. So we compare every pixel in that picture, and if it's greater than the threshold, we change the pixel value to 0 or black, and if it's less than the threshold, then it stays at white.
Yep, and as you can see, it worked over here. So in our plots, we have like our original color image, our grayscale image, our blurred image, our edge enhanced image, and then finally the final thresholding image. And you can go in and save these by just right clicking and then saving the plot. And to show that this works on another file, we will be showing this, and this one should take a little less time because it is smaller. All right, and so as you can see, this also works for a different image. So this one we use the Purdue Bell Tower. So all of the images, the color, grayscale, blurred, edge enhanced, and the thresholding image all work. As you can see, it's a little darker and more like it's a little clustered, I guess you could say. So the user could easily go in and adjust this one number to create a threshold that meets more of like their desired ratio, I guess, for their image and like what their specifications need.